Welcome to the inaugural episode of the AfterMath podcast, the official podcast of the Math Citadel. I'm Jason Hathcock, and I'm an editor, researcher, and designer for the Math Citadel.
And I'm Dr. Rachel Traylor. I'm the founder and lead mathematician at the Math Citadel.
So today we're just going to introduce who we are, what the Math Citadel is, and our backstories. So for me, I got my start in math back in Texas, where I'm from. And I went to the University of Texas at Arlington, eventually entering into the graduate program in mathematics, so a doctoral program. And that is where I met Dr. Rachel Traylor.
Well, I wasn't doctor then when we met. I got my start, actually. I was intending to become a chemist at Georgia Tech, and then couldn't put the math down. Ended up getting my bachelor's in math. I'm working for Lockheed Martin for a little bit while I was working on my master's in stat at Georgia Tech. I realized that I really did want to do research in mathematics. It was a daunting thing to consider, and I decided to make the leap and do it. So I ended up at the University of Texas at Arlington to work on my doctorate because, hey, they funded me, so that's cool. And that's Jason and I met, in fact, both of our first semesters there.
So in the course of doing my research in applied probability theory for my doctorate, I realized that academia was what I was being pushed towards as a career field, and I didn't want to do that. I wanted to actually take the things I was learning, and I wanted to put them to use, put them to work in industry. And so I decided to move out to Silicon Valley where I could do that.
And I did finish, I finished mine. I did my dissertation in reliability theory and stochastic analysis. Some of the chapters of my thesis are currently being published on the Math Citadel, and we'll work on some explanatory videos for some of those. And I moved out to Silicon Valley after I took a job with what is now Dell EMC, but it was EMC at the time. And I worked there for about a year and a half as a mathematician there. And then I got let go. But now the Math Citadel is my full-time gig.
I'll say that whenever I got to Silicon Valley and I started looking for places to apply what I'd learned, what I saw mostly were applications without a big emphasis on what was being applied.
Yeah, I agree with that. I worked in the storage industry for a while, and boy, without information theory, the industry wouldn't exist. But nobody cared about the math behind that anymore. You take, frankly, what can be a bit ill-defined terms and concepts, and you continue to build on them. But I noticed that the appreciation for pure math, as opposed to what is now considered data science, was a bit lacking. So my goal, partly in founding the Math Citadel, was to change that a little bit. Part of the problems are most of the things that exist to get people involved in mathematics are aimed at children. They're aimed at children, and they're either aimed to be entertaining or as a chore or as a tool set. And we don't believe that about mathematics. We think that leaves a lot to be desired. There are topics in mathematics that you don't need a doctorate to touch and understand and apply.
And which have great applications
Correct.
to industry.
Correct. Coding theory, group theory. We publish some of these articles on our site. And we also are aiming to talk with other companies and try to dig in a little bit behind their technology and really address some of the fundamental math that's behind these in a way that shows that math is useful. And it's useful not just in making sure you get a good engineering degree, but it has implications for your business and your innovation. And it's just pretty.
Absolutely. You can rest assured that if you're working in industry, mathematics is working in the background of what you're doing.
And not in a sense that it's been done, so why why care about the pure math anymore? We don't believe that. We believe that at its heart, innovation starts with mathematics. In fact, I think one of the nice analogies I've seen about how mathematicians think, because we do work slower. I promise you, I can't get papers out every 2 weeks. If I were that good, boy, I'd be somewhere at a really nice university, I guess. But
takes a little longer.
But what do we get with it? One of my papers produced 3 patents. We work a little bit slower. That's true. It's like building a bridge. If you need to get across somewhere really quickly, you can do it. In fact, you can probably just throw some really big rocks in the water and jump right across. And you'll get across. But if you then try to build off of that foundation, and all you had were a few rocks that might have been a little wobbly, eventually, whatever structure you built on top of that to continue moving large quantities of whatever across that bridge, it's going to fail. Unless you go back and really solidify those foundations. That's what mathematicians do. We build bridges slowly out of stone by hand, but they will last you for generations. So, what else do? We also recognized the need for book reviews.
Everybody's looking for a good source whenever they're trying to learn.
Sure. And man, if math books might not be one of the hard, like turning it over and reading the jacket, not going to help you very much.
A good book can make all the difference.
Oh, yeah. Oh, big time. In fact, I think if I had learned algebra out of a book that wasn't Hungerford, I probably would be a lot better at algebra now. Now, we've actually put up a review of a very good introductory algebra book, but yes, it can make or break someone's interest in an entire topic. And so what we try to do is bring these book reviews to you. We make sure we've either read, taught out of, or studied out of every book that we put up there, cover to cover.
When I think of all the time I spent carrying around Apostle.
Oh, Apostle is, yeah, that's an analyst's Bible, I think. Just fundamentally, if you want to learn how to think like an analyst, that's the book to go with for sure.
Mm-hmm. Great reference.
We also, plan to bring some discussion of other papers, not just mine, although mine are wonderful.
Yes, they are.
Of course, I'm going to think that. I spend months or years on them.
But we encourage contributions from other authors.
We encourage contributions from other authors, and papers of value or even just interesting ones. We plan to write on those in a format that helps you understand what was actually going on there and what some of the implications are of the papers, right? Not just the fact that they exist, but try to help facilitate some amount of brainstorming about the implications of what was proven or discussed in some of these papers.
We hope to bring an appreciation of mathematics to the business world.
Part of it, I think, is going to be a little bit of a cultural shift. It's an appreciation for slowing down some, which is a little antithetical to what the typical business philosophy is today.
Drive towards forward movement as quick as possible.
If you move forward too quickly, how do you know if it's the right direction to go in? One of the things I found when I was interviewing at other companies after I got laid off was this desperate drive for anything, something, create an algorithm, like quickly do something with a data set. And I don't think in the long run that's the right approach. I think backing up just a little bit, understanding the problem, and looking for a solution that is generalizable, analytical in the sense that it's not data set dependent. A lot of these machine algorithms that we rely on so much and that are fairly easy to implement are ultimately data set dependent, problem specific. If you change the problem just a little bit,
it kind of collapses.
Your solution is no longer useful. I think that boils back down to you can't put research on a development cycle. It's not possible. Innovation cannot be put on a development cycle, and it can't be put on deadlines. That's advanced development. But pure research is becoming a bit of a lost art. And for my philosophical beliefs, that's something of what I'd like to bring back. That funding that independent exploratory research that is guided by and inspired by real problems. I'll give a particular example because now it's getting philosophical and a little idealistic. One of the things that I worked on was anomaly detection. And what do we mean by anomaly detection? Good luck. We have an article on talking about that. Why is it such a contentious problem? Everyone wants to detect them, and we all have a good, we'll call it, feel for what it is. It's stuff that's weird, whether it's a potential ransomware attack, potential fraud, potential strange issue in your metadata, potential outage, whatever it is. We want to know what it is so we can do something about it. One thing that I noticed with a lot of the current anomaly detection algorithms is they violate a lot of general assumptions, especially for time series, and they're not really objective, right? They require you to decide what kind of tolerance you want, or what kind of distance, distance away from what is normal, which of course you have to model first.
For sure. A person sees an anomaly and they know it, but they only know it once they see it. Right.
And if I showed you a picture, likely you could pick out something that looks weird. What I looked into, so the notion, and without getting too mathematical, because this is our introductory podcast, the notion of ARIMA modeling has been around in time series for a long time, and it is formally defined. The model is formally defined, and estimating the parameters has decent implementations. Even the notion of anomalies or interventions has formal definitions. What ended up happening was, in practice, when we tried to implement that on real data sets, we ran into problems. The more complicated the model, the harder it was to be able to detect anomalies. And that inspired digging into and finding a paper that moved to a fuzzy number space that took an extremely complicated ARIMA model and made an extremely simple autoregressive model. Nobody's really done anything since then, and going down this exploratory path can have massive implications for analytic anomaly detection, real things. Though, if I twisted it and just simply said, I'm studying fuzzy numbers, most people wouldn't see the point. But it was inspired by a real problem.
The studying of those fuzzy numbers is what brought about the idea for the more elegant solution.
Correct.
So that application of pure mathematics brought about an industry appreciable solution.
Well, I'm still working on that industry appreciable solution. Maybe that was a bad example to start with because I still have to build it out. I don't have any proofs yet on it. What I can see down the line is massive implications for the ability to classify formally types of anomalies in time series, and the probability that the next data point or today's current data point that you see is one of those types of anomalies or nothing at all, and the probability that it is one of those. It gives you a way to rank those by likelihood and then make decisions.
And this is a solution that is extendable.
Right. Well, yes, my goal is it's for any time series. I don't care if it's your system metadata. I don't care if it's something to do with Twitter. I don't care what it's for. It's just...
You can do away with those limitations.
That's the goal, because everyone that's talking about anomaly detection, to continue our analogy, fundamentally, they're all, I realize there's other kinds, right? There's multiple dimensions, but let's just stick with time series because there's a million varieties of those. They're all ultimately the same. A time series, it doesn't matter what the time series is of, it's still a time series mathematically. They're fundamentally all trying to solve the same problem. So if you back up and not just take an algorithm that learns your particular data set, and back up and look at the problem from an abstract notion, you can create an elegant solution through abstraction that can then trickle back down to all of these other applications with very little additional adjustment other than parameter estimation. That's the goal.
And that's what we're trying to do at the Math Citadel.
And we try to, instead of just putting papers out and just, here you go, we do want to, we'll partly use this podcast to explain and discuss motivations and implications for some of the papers on this site. And we'll probably also discuss some certain philosophical questions, and maybe we'll get Jason to give us some of his artistic outlook on fun small things, typography and photography.
I can go on so long about typesetting.
Things like that. So these will be the types of topics that we aim to discuss on this podcast. Go check out the Math Citadel for all sorts of other stuff. We're always looking for suggestions on topics. If you have a topic that interests you, if you have a paper you found interesting and either want it explained or want to understand it, if you're interested in applications of the research, contact us. Go to themathcitadel.com/contact and send us an email. You can also find both of us on Twitter. My handle is @mathpocalypse, and Jason?
I'm @jasonographer.
So tweet to either of us and we'll be sure to answer and get back to you. And until next time, thanks for listening.